This is the Tomahawk cruise missile, one of the greatest prides of the American Navy. But what makes it so special? Isn't it just a big missile? Well, no, it's much more than that. It's a true aeronautical engineering marvel. The Tomahawk cruise missile is powered by a jet engine, like an airplane, and can be launched from submarines, even if submerged, or from surface ships, like destroyers. It's designed for absolute precision, has a range of over 1,500 miles, and is equipped with a data link that allows it to change its course in mid-flight if necessary. When the Tomahawk reaches its target, it can be put into standby mode, flying in circles over the target for hours while waiting for the ideal moment to strike. It can also fly extremely low, about 15 meters above the ground, to avoid detection by radar systems. It has an advanced digital system that allows it to navigate around natural obstacles like mountains and man-made obstacles like buildings and houses. But how does the Tomahawk accomplish all these amazing characteristics that make it so efficient? The history of the Tomahawks began in the 1970s in a partnership between McDonnell Douglas and the Applied Physics Laboratory in Maryland. The idea was to create a cruise missile that could avoid enemy radar's detection and fly at subsonic speeds, that is, speeds below the speed of sound. To avoid radar detection, the missile can fly at very low altitudes of about 50 feet, since at these altitudes the radar waves are usually blocked by buildings or mountains, thus giving a huge advantage and a practically undetectable flight to the missile. It should be able to carry 450 kilograms of conventional explosives or a W-80 type nuclear warhead with a destructive power that could vary between 5 to 200 kilotons. To give some perspective, that is a little more than 3 times the power of the Hiroshima bomb. A Tomahawk model typically has a length of about 20 feet, including the booster, a diameter of 1.8 feet, 8.7 feet of wings, a mass of 2,866 pounds or 3,527 pounds with the booster, and can reach a maximum cruise speed of about 577 miles per hour, which is about the same speed as a jet airliner. The Tomahawk is launched vertically from special compartments in cruisers and destroyers. In the initial launch phase, the Tomahawk is powered by an extremely powerful solid-fuel rocket engine that operates for about 10 seconds and propels the missile from the compartment to a few kilometers away. Then this rocket engine is jettisoned and the Williams International F-107 WR-402 turbofan jet engine comes into operation and propels the missile to its target, which can be more than 1,500 miles away. This engine uses a fuel called TH-dimer, which is also one of the components of the fuel used in aviation. When the missile is launched, the center fins as well as the rear fins are retracted so that the missile becomes more compact and occupies less space inside the launch tube. A few seconds after the launch, the fins are extended and begin to generate lift. The Tomahawk employs a cylinder design, and internally it is composed of an infrared seeker, guidance devices such as inertial navigation systems and GPS, a terrain control matching, a digital scene matching area correlator, and a time of arrival system. Behind them is the data link, a device that maintains constant two-way communication via satellite between the missile and the command center that sends instructions such as the target, trajectory changes, among others. Right behind the data link is the missile's explosive charge, which can be conventional explosives or, in the initial versions, a nuclear warhead. In the center is the tank containing the fuel that will be used to propel the missile during flight. On the outside are wings to generate lift at the rear, and underneath is a retractable air intake that provides air to the missile's engine. The engine is angled slightly downward to improve the admission of air coming from the intake. At the rear is the exhaust duct of the engine and fins for stability and attitude control during flight. Also at the rear is the solid fuel booster to make the initial launch. The initial phase of propulsion is done by a solid fuel rocket engine for a few reasons. The first is that these engines have a lot of thrust. This is very necessary, especially in the initial phase of the launch, where the missile is vertical and much heavier since its tanks are full of fuel. The second reason is that solid fuels can be stored for years, maintaining an excellent state of complete readiness. And the third reason is that the missile can reach high speeds in a short time, which makes it get to the target much faster, and the high airflow facilitates the ignition of the jet engine. Now that we know the basics about the missile, comes the most interesting part of how the Tomahawk flies, finds the target, and how it knows that, in fact, it is its correct target. Everything starts before the launch with the TTWCS, Tactical Tomahawk Weapon Control System, an integrated system with the navigation, communication, situational awareness, and launch systems of the ship that computes, among other things, the trajectory of the missile to the target. Many past missiles used inertial systems and GPS to find targets. However, using only these systems, the precision rate of the missiles is around 30 feet. That is, the missile could miss the exact point of the target. To circumvent these problems and increase the precision of the sophisticated navigation and guidance systems, some other technologies are used, such as TERCOM, or Terrain Contour Matching, TOA, or Time of Arrival, and DISMAC, or Digital Scene Matching Area Correlator. First, the missile uses TERCOM. In this technique, the area or terrain through which the missile will pass is divided into several sectors, and then this difference in height between each sector is used to generate a digital map that goes in the missile's computers. These data are usually obtained by satellites that do mappings. During the flight, the missile uses a radar altimeter to measure these height differences and compare them with the data stored in its memory. In this way, the missile knows if it is on the correct trajectory, and if necessary, the missile makes corrections in its course to stay on the correct path. However, this technique does not work when the missile flies over the sea or over certain regions in the desert, where height variations are very rare. In the past, many Tomahawks deviated from areas with few height variations in the terrain and followed another path to the target. However, this made all the missiles follow exactly the same route, making them easy to be shot down, which happened in the Gulf War. To control these problems, in addition to GPS, DISMAC was introduced. In this technique, a camera is used to take photos of the terrain and compare them with photos stored in the missile. The variations in height in the terrain are not relevant, and it greatly increases the precision of the missile, since buildings and houses can also be recognized by the system. Only photos of the target and its surroundings are inserted into the missile's system, since it would be very difficult to input photos of the entire route of the missile. However, variations in climate, rain, snow, among other conditions, can cause a great difference between the photos stored in the missile's memory and the photos taken at the moment by the missile. Therefore, in the most recent versions, the Tomahawks have the Imaging Infrared Seeker, a type of seeker that makes readings of the terrain while the missile flies and allows it to recognize and find the target regardless of weather or visibility, since the camera uses infrared. This also allows you to check if the target was hit or not, since the data is sent to the control center of the ship. With all these systems, the precision of the Tomahawk missiles has increased a lot, and historically the precision rate is around 16 feet, allowing them to fly extremely low in inhabited areas or in strictly protected areas. Upon approaching the target, the missile lowers the altitude to 100 feet or less before impact. And speaking of impact, the Tomahawks do not need to hit the target for their explosive charge to be detonated. It is enough to approach the target at a set distance or to a pre-established altitude. The fact that it flies at relatively low speeds compared to other missiles and has wings to provide lift allows the Tomahawks to gain greater efficiency in fuel consumption, which is why they can fly long distances of more than 1,500 miles. This also allows them to be much more maneuverable compared to supersonic and hypersonic. In addition, the ability to fly at a non-linear route to the target makes it stand out from other missiles. The Navy version is launched underwater from submarines with a system that uses high pressure to expel the missile a few meters above the water. Then, its solid fuel engine immediately enters operation to propel the missile. This first phase is very short, and the operation of the jet engine begins. In addition to all this, it is a relatively cheap missile situated in the range of $1.5 million, compared to other cruise missiles that can cost up to $3 million. The Tomahawks have a lifespan of 30 years, but after 15 years without being used, they go through a process of evaluation and certification and re-enter service. There have been about 8 variants of Tomahawk since their entry into operation in 1983. The BGM-109A variant carried a W-80 type nuclear warhead, but it went out of operation in 2013. The LGM-109B variant was an anti-ship version, and the BGM-109G variant was launched from the ground and carried a W-84 type nuclear warhead, but it went out of service in 1991. But beyond the variants, the Block 4 version is the one that is currently in full operation in the United States. This version allows the missile to receive data from multiple sources such as airplanes, drones, satellites, oil tankers, armored vehicles, and ships to find its target. It also allows the course of the missile to be changed to one of 15 pre-established points and redirected to a new target. In this version, the missile's ability to enter standby mode and loiter over the target at a safe distance until it receives the command to attack was introduced. Or in case of attack cancellation, it can go to a pre-established area to self-destruct. In addition, it obtains data on its health among several other data through the direct two-way link with the satellite. But this version will gradually be replaced by the Block 5 version, which entered operation in 2021 and includes many more improvements and sophisticated features.